Okay, so we talked about how we can hydrogenate these alkenes. Okay, and we have ever seen this reaction. Okay, then we named this. Now for those who are absent, I told you that whenever you see this, then that must be a carbon atom. So at each corner is a carbon atom. Okay, a carbon atom. So this one is 1, 2, 3, 4, 5, 6. So this one is hex. Okay, then this is a group that is attached. So the group is attached on carbon 2. So when you're naming, this one becomes 2-methyl hexa 2,4 diene. And so we say this reaction is important in industrial chemistry in that we can use it to synthesize the fats, and one of them is margarine. Where in synthesis of margarine, if you check your margarine, I have it here, yeah, you find there hydrogenated fatty acid. Okay, hydrogenated fatty acid. What does that mean? It means that now if you studied chemicals of life, you talked about types of fatty acids, where you talked about the essential and non-essential. But as if that's not enough, you went ahead and talked about saturated fatty acids and unsaturated fatty acids. Now this is, if this is a fatty acid, let me just remind you, fatty acids, it is just H, and then it is a long chain of a carboxylic acid. So this is the carboxylic acid, the rest it is a hydrocarbon chain. So there are some fatty acids such as omega-3 and omega-6 fatty acids that are saturated. They have a double bond. Okay, they have a double bond within their carbon skeleton. So they get these saturated as fatty acids, then they hydrogenate them, okay, to produce saturated fatty acids, which can now be condensed and form the margarine. And these ones have health complications. Okay, they have different cardiovascular issues. Okay, but we are not in fatty acids, we are not in chemicals of life, so I won't dwell more on that. Then another reaction that these alkenes undergo is halogenation. And it is simple, they react with chlorine or bromine or iodine. Halogens are group 7 elements, okay? So they react with chlorine, bromine, and iodine in presence of an organic solvent. Now there must be an organic solvent such as tetrachloromethane. Or you can say carbon tetrachloride to form a dihalide. And in this case, it is a vicinal dihalide, like how we see. So halogen, now the mechanism is, if a halogen approaches, okay, this pi bond, are we together? Then the halogen, which is, okay, let me use chlorine. The halogen, which is a diatomic molecule, it is believed these two atoms, being atoms of the same element, they do have the same electronegativity. So it is believed that they must share these electrons. They must undergo homolytic fission. But that's not the case here. That when this halogen approaches a pi bond, okay, then this halogen molecule, somebody wants to be admitted, it is going to be induced, okay, to form partial charges. That the halogen or the atom that is close to the pi bond gains a partial positive charge, and the atom or the atom that is far away from the double bond gains a partial negative charge, and so it will be able to undergo a chemical reaction. Okay, as you can see this reaction. Now let me first go and admit this. Let's talk about the mechanism. Let's write the mechanism. And somebody told me that for them they cram mechanisms, and I didn't understand what you mean by cramming a mechanism. How can you cram a mechanism? Anyway, let's write our equation. So it is, let's say ethene, for the benefit of the writer, let me just use ethene. It will react with our halogen, and in this case, let's use chlorine, in presence of carbon tetrachloride. Now the reaction takes place at room temperature. Here you don't need to heat. Okay, so what do you form? The chlorine, there is a 2 here. The chlorine adds itself across a double bond, and you end up forming a vicinal dihalide. So there is a 2 here, then a Cl, then a single bond, and then CH2, and finally Cl. So that is the equation. Now the next thing is to propose a suitable mechanism. And the mechanism is simple. If the halogen approaches a double bond, okay, or a triple bond, because it is the same, okay, with alkynes. So if our halogen approaches a double bond, for example, that will be our halogen, the carbon, sorry, the chloride with a chloride. So the double bond here, it will induce this molecule to undergo polarization, okay, to gain partial charges, okay, that the molecule that is close to the double bond gains a partially positive charge, and the molecule that is far away from the double bond takes the electrons and gains a partially negative charge. Okay, so as a result, this one becomes an electrophile and this one becomes a nucleophile. So you can use this reaction as an example of an electrophilic addition reaction. Is that okay? Yes. So as a result, after this one has gained partial charges, let me first do the cleaning. I remove this one. That's pretty good. So after that one, after our chlorine molecule has gained partial charges, then the partially positive chloride atom, which is an electrophile, is going to receive electrons, okay, from our ethene molecule. Now if this one receives electrons, then the electrons, the 2 electrons that we are making the chloride bond, are taken away by this chloride atom. Is that okay? Good. And so what do you form? We shall form our CH2, our CH2, the double bond goes, and then CH2, CH2 with a chloride molecule. But now, look here. Remember the other concept I told you? Carbon must have 4 bonds. It can't go below 4 bonds. It can't go above 4 bonds. So look at this. It has 1, 2, 3, 4. But look at this. It has 1, 2, 3. So it has lost the electrons. So because it has lost the electrons, to balance the bond, then it gains a partial, sorry, not partial, but it gains a positive charge. So if you don't write that positive charge, you cannot get any marks. Is that okay? Yes. Now, our chlorine, after gaining the 2 electrons, or our chloride atom, after gaining the 2 electrons, it gains a full negative charge. So in this case, our chlorine now is a nucleophile. It is electron rich. So therefore, what is going to happen? Since this one has enough of electrons, and this one is jutating, jutating, it is not, okay, it comes from guttation. Guttation means dropping of water droplets from the leaves, So that's why I use jutatation to mean crying, okay? So don't get puzzled. So since this carbon atom is crying, it is electrophile, it is electron deficient, and this one is electron rich, then this one will donate some 2 electrons to this carbon. Is that okay? And so as a result, you form your molecule, your compound as Cl, then CH2, CH2 with a single bond, and then CH2, and finally Cl. So it is as simple as this. That is the mechanism. Now, take note. If you write your mechanism and you don't put these partial charges, you cannot get the mark. You don't put this partial charge, you cannot get the mark. The arrows, they must have where they come from to where they are ending. Do you see how my arrows are touching? Do you see this? Do you see this? So they must have where they come from and where they end to. Is that okay? Yes. So in case you have a question, you can always drop it in the chat box. So can you try out this? Try out this because we are here to practice. Try out this. Yes. Oh, sorry for this. Let me see if I can. Because the line was continuous, that's why the whole of it had to go. But it is okay. So you try out this. And then there is a double bond here. And then there is a C. Try out this. Hurry up. You react it with chlorine in presence of carbon tetrachloride, or you can say tetrachloromethane at room temperature. Hurry up, please. Hurry up. Hurry up. First, write the product. You name it and drop the name in the chat box. There's something I'm interested in. Hurry up, please. Hurry up. We are here to practice. Write the final product. Then you write the IUPAC name and drop the name in the chat box. Now make sure when you're writing, your symbols must be okay. Don't write your CL as. Okay, let me use this part. You write CL as. And that's your CL. This is wrong. You write your carbon tetrachloride as this. My dear, this is wrong. This is wrong. Okay? The C must be of the same size because they are all capital C's. And then the L, it is a small L. Okay? So that is now. And then the 4 must be subscripted. So now this is carbon tetrachloride, but not this. This is not Cl. When you are writing this with a pen, let all be of the same size. Okay? The corners must all be having same size. Not so? The arrows. The arrows. So I hope you have finished. Be our final product. Okay? So you have a methyl here. Okay? You will have a Cl here and a Cl here. So if you have this as your final product, you mark yourself here. So Deo, according to what you gave me, this is it. Now the mechanism is simple. As usual, you write your cyclohexene. That's good. Your methyl cyclohexene. Then the Cl. Then this will be partially negative, and this one will be partially positive. If you don't have the partial charges, then something is missing. So from that, then this one will donate these pi electrons to this chlorine. Okay, the arrows must be touching. If your arrows are not touching, then something is missing. Then you form. Now, this is what I was interested in at that stage. Now, after writing that Cl, okay, sorry for that, and you have your methyl, okay, your methyl. Now, where is the Cl going to attach? I'm sure some of you put the Cl here, others put the Cl here. But which chemistry governs where the Cl is going to attach? Now in this case, the Cl is going to attach on this carbon here. Why? Because there is a possibility of forming a tertiary carbocation. So you put a plus here. So this one is a tertiary carbocation. This carbon atom is surrounded by this bond, and this bond, and this one. So this is a tertiary carbocation. Whereas when you put your carbon, let's say if you put your carbon, your chlorine here, you form a secondary carbocation, which is relatively unstable compared to the tertiary carbocation. So if you wrote this, still mark yourself. If you put the chloride here, then there is something small that is missing. Then the next step is the chloride. Now it shouldn't be, there should be a space because those are two different letters. Now the chloride, it will donate its electrons because now it is a nucleophile. So it will donate these 2 electrons to this carbon atom. Okay? And so as a result, you form this as your final product. So there is CH3, then you have a Cl and another Cl here. So if you have this as your final product, bravo, congs. Okay? Now when you are naming it, now the chloride is preferred compared to a methyl group. But we have 2 chloride atoms. We have this one and this one. So which one is going to be taken as? Which carbon atom is going to be taken as number 1? Of course, the one that will give us the lowest sum, okay, in the locants. And automatically it will be this one. So the name that they will give us is probably correct. So let me see what sum of us occurs for all halogens apart from fluorine. Why fluorine? Because fluorine is highly electronegative. Okay, so it becomes hard to react with carbon. But for chlorine, for Br2, okay, for iodine, okay, you form a dihalide. But you form that one if you react, if that reaction is taking place, or takes place in presence of an organic solvent. But if you react it in presence of water, or if you replace water, if you replace the organic solvent with water, then you form a different thing. Okay? You form a totally different thing. So if the reaction is done in presence of water instead of an organic solvent, then the product formed is a hydroxyl alkene. Okay? Not a chloride. Why? You need to know the science, because this is now the science. I can say explain why reaction of bromine in presence of carbon tetrachloride form a dihalide, but when I replace the carbon tetrachloride with water, I form hydroxyhalogenalkene. Now you need to know the science, and the science is simple. Because you are reacting bromine in presence of water, after addition of the bromide atom onto the chlorine, then we shall form the bromide ion. Is that okay? Which is a nucleophile. But in the same reaction vessel, you will have there water. And this water is also a nucleophile. Why? You have two lone pairs of electrons on the oxygen atom. So these lone pairs of electrons can easily be donated. Okay? But because the water is in large excess, okay? Because this water is in large excess on addition to these two lone pairs, then the water or the OH ions generated from this water outweigh the Br, the little Br ions that are formed within that reaction. And so instead of the carbocation formed getting electrons from this, it will get electrons from water. So as a result, you end up forming a hydroxyl halogeno alkenes. Let us see the reaction. So we don't have the reaction. Okay, let's see the reaction. Reaction of CH2, okay, CH2, CH2. This is ethene with bromine, bromine water. It is Br2 in presence of water. Okay, in presence of water. What do you form? Instead of forming a dihalide, then you form CH2, CH2 with your Br here, and then CH2 with your OH. Okay? And so when you are naming this, which one becomes carbon 1? Yes, automatically this one. Why this? Because the OH, if you have both the OH and the Br functional groups present on the same compound, then the OH is preferred. The OH is highly electronegative than this. So it is preferred. So that carbon with the OH functional group becomes carbon 1 and this one becomes carbon 2. So when you're naming, therefore this one becomes, let's name together. Yes, 2, brilliant, and then, yes, bromo, bromo, 2 bromo, then from bromo, then this is ethanol, as simple as that. How do we name alcohols? We get the stem name and then we add the word OL. Let me first moisten my hands. So that I can write well on the board. So now the mechanism, it is simple. Let's write the mechanism. Can I erase everything? No, it won't be good. So this is a highlighter. Let me erase this. Let me erase the name. Okay? So that I can use this part for writing the mechanism. Now, anyway, this part is going to be enough. Let me use some different pen. So the mechanism, it is still the same. The CH, CH2, okay, then the CH2, then when the Br approaches, oh my god, what is that? Approaches a double bond, okay, it will induce the double bond here is going to induce this Br to form partial charges, where that Br that is close to the double bond gains a partial positive charge. You must show the partial charges, okay? And then the other one, which is far away from the double bond, gains the partial negative charge. So as a result, this one will donate the electrons to this electrophile, and so this one will end up taking away the 2 electrons. Is that okay? And so what do we form? We shall form CH2, CH2 with a single bond, and then CH2, and then Br. Is that okay? But the other concept of ours, carbon must have 4 bonds. But you see this one, it has 1, 2, 3. So to balance the both, then we shall put a plus. And this plus indicates that this one has lost the 2 electrons. Now this is where the science comes in. The other one, in presence of an organic solvent, it is this Br that is present as a nucleophile. But in presence of water, okay, if you replace the organic solvent with water, then the water becomes a nucleophile. In other words, in your reaction vessel, you have both the Br as a nucleophile and water as a nucleophile. But because water is in large excess, okay, then water is going to outweigh this Br. That it will be the one to donate its electrons. So you can represent this as this, okay? So even if I write this, it is all water. So this is O, not D. So you put your lone pair of electrons, and then you get your arrow, which goes to this carbon atom. Are you seeing? So this oxygen donates the electrons to the carbon atom instead of the Br. So as a result, what do we form? We shall form, yes, let's write it together. I hope you are writing the mechanism. Don't cram. This is CH2. Oh, this is, I was just writing a bond, eh? It's not the same. Then CH2. So with organic chemistry, you must be careful. If you are writing for your exam and such happens, then you cross and write again. Then there is a Br, and then the water has attached itself here. But hey, see, the water has 1 hydrogen, okay? And then it also has another hydrogen. So you see, oxygen has a maximum of 2 bonds, okay? Because it has 2 outermost, so it has 6 outermost electrons, so that's a valence of 2. So it can form a maximum of 2 covalent bonds. But you see our oxygen here, it has this, it has this, it has this. So to balance the charge, to balance the bond, then you put a plus on oxygen. So this plus indicates that the oxygen has lost 2 electrons, which are these ones that it has donated to this. Is that okay? Yes, that's brilliant. Now, this oxygen cannot exist like this. So as a result, it is going to lose a proton. Now, what is a proton? If you remember, a proton is that hydrogen that has lost its electron. It has 1, but even that 1, it loses it. So it gains a partial, so it gains a positive charge. So in this case, this oxygen is going to lose a proton and it will take away the electrons, okay? And that's how we are going to represent it, okay? And so you put minus a proton here, as simple as that, minus a proton. Now when you are writing this, it shouldn't cross. Always be as careful as possible. Then what do we form? Yes, we shall form our CH2, our CH2, 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 with a Cl here and the OH. Is that okay? Yes. And this is our final product instead of the other one. So please make sure you practice as much as possible. Actually, I promised to send questions, but
Teacher,
this, yes, so team.
where does the chlorine come from?
Where? Oh, this
As
CL.
the chlorine come
Oh,
from?
that's a good question. That's a mistake. It's just a miscons. It's just a mistake. It's supposed to be the Br? That's a good question. This, then you have a 2 and Br. Yeah, thanks for that observation. So if you are writing for chlorine in presence of water, it is still the same thing. You put the Cl. If it is iodine in presence of water, still the same thing. But in tetrachloromethane, which is an organic solvent, the only nucleophile is going to be the Br minus generated. So it will be the one to donate. So you form a dihalide. Thanks for that correction. Thanks for that question. Shows that you are attentive. Yes. Let me check the chat box. You never know, there might be questions. Okay. Reaction of alkenes with halogen acids, HX. Now, it is also an electrophilic addition reaction. Why? Because there is an electrophile that will receive electrons from the double bond, but is also an addition reaction because the compound, this halogen acid, just adds itself to form a saturated compound. So alkenes react with halogen acid to form halogen acids to form alkyl halides. As you can see from this reaction, you have your alkene, okay? You react it with a halogen acid such as HBr, you form bromoethane, or you can say ethyl bromide, and the reaction is simple. The mechanism, is simple. To be CH2, CH2, okay, plus the HBr, HB. Now, here the hydrogen and the bromide atoms, they have different electronegativities, where the Br is highly electronegative than the hydrogen. So as a result, the Br is going to polarize this hydrogen Br bond, okay? That it will end up creating partial charges within the HBr. And the Br, therefore, since it has taken the bonding electrons, it will become partially negative, and the hydrogen will become partially positive. And so this hydrogen, which is partially positive, is what we call an electrophile. It is electron deficient. So as a result, it will receive electrons from the pi bond. These pi electrons that make up this double bond, they will be donated to this hydrogen. Now, don't do this. Most people they do this. No, this is not correct. Don't do this. But still, don't do this. Don't use a straight line. That is also not correct. But don't exaggerate. So, this one will donate the pi electrons to this hydrogen, and as a result, this HBr bond is going to break. Okay? And all the electrons will be now taken by the Br. So as a result, what shall we form? We shall form CH3, okay? And then CH2. Is that okay? But now see, this one is okay, but this one, carbon, the concept is one. I will always emphasize this. The concept is one. Carbon must have 4 bonds, not below, not above. So you find somebody writing this and somebody puts a plus here. Now you wonder, this is for the people I teach, there is a word I like, and they usually say it whenever they see me. I usually say this is madness, and this is really madness. Why are you putting a plus here? Let's be realistic. You are a chemistry student. As per now, there are mistakes that you should not make. If I find you with a plus here, then I don't know what to call that. Okay? So because this carbon, it has 3 bonds. Which 3 bonds? Let me try to spread it. It is like this. One, you have one hydrogen here and another hydrogen here, okay? And another carbon bond. That is it. But carbon must have 4 bonds. Do you know why I'm emphasizing this? You find somebody putting a plus here and you wonder. Or you find somebody with this without a plus and you wonder. So because this carbon has 3 bonds, it means that it has lost electrons. So it gains a positive charge. Okay? So you put a positive charge on this carbon. If you don't put it, then you cannot get any mark. So now after writing this, now this carbon is electrophilic. It is mutating. It is crying, it needs some electrons. Then the Br comes in. Okay? Now the Br, remember it received 2 electrons from the HBr bond, so it is now fully nucleophilic. Okay? So it will donate the 2 electrons to this carbon. Not so? So as a result, what do you form? Don't use a straight line. At least mine has some curve. What do you form? Then you form CH3, CH2, and then Br. So it is as simple as that. That is a mechanism. Okay? Yes. Good. Now, I'm going to erase the whole of this. Okay? I'm going to erase the whole of this. Now, addition reaction can proceed in 2 ways according to the conditions of reactions, depending on the conditions given, and also depending on the reaction that you are carrying out. Okay? The first way is that one which you have just done. In absence of a peroxide, it follows an ionic mechanism, and you have seen me writing the mechanism where I was putting partial charges, and I end up making the ions, the bromide ions. So that is what we call an ionic mechanism. However, in presence of a peroxide. Okay? Now, before we talk about a peroxide, there is something I need to introduce to you. Some new concept. Now, how about in this ionic mechanism? Here it was easy. It was a symmetrical alkene. What do I mean by a symmetrical alkene? All the carbon atoms have the same number, okay, of hydrogens, not so, attached to them. Even when it is like this, R, then C, then double bond, C, then another R. So even when it is like this one still remains asymmetrical. Now this English. This one remains asymmetrical. Okay, there is a space, alkene. This one, because this one has 1 hydrogen, and this one also has. In other words, the number of hydrogens are the same. But however, the same reaction can be carried out on an asymmetrical, okay, an asymmetrical alkene. Now here the A, this is the opposite of symmetrical. Asymmetrical, like one carbon has more hydrogens than the other. Okay, then here we follow the Machonikov or Machonikov. This, he was a Russian scientist, so Russian you can call him Machonikov, but if you want to English his name, then he becomes Machonikov. So you any Makes sense. So here we use Machonicos rule. Now in your mind, you should be asking yourself that what's up with this Machonicos rule? Machonicos rule. What's up with it? How is it? What is it about? How do you even state it? And it's there. It's now. I need your attention here because this is science. This is science. You remember the other synthesis we did, okay? Where on the final we are preparing alcohol and we used acidified water. Let me write it to remind you just. So we are preparing alcohol and we had this CH, a double bond. There is something here. Let me just a reminder. If you want, there is a video you can go and watch it. It was CH2. And we were preparing this and we wanted to form a primary alcohol. Okay? CH, CH2, CH2, then OH. Now, this rule is important. That you remember I used the peroxide. I added acidified water and warmed, but I added the peroxide. Okay? Why? The peroxide opposes the Machonicos rule. We call it the anti-Machonicos. Okay? So what's up with that Machonicos rule? So it states that in a reaction of an halogen acid with an symmetrical alkene, or you can say with an asymmetrical alkene, okay? Then what happens? The hydrogen is added to the carbon atom with a higher number of hydrogens. Okay? Mark this word. The hydrogen is added to the carbon atom with a higher number of hydrogens, and the halogen atom is added to the carbon atom with a lower number of hydrogens across the double bond. If you know that, then you are good to go. Let me first interpret it before I give you another version. You can, this is what it means. You are reacting with this. Then you have a 2 here. Okay? And then there is an alkyl group. So this one is an unsymmetrical alkene, where this one has 2 hydrogens and this one has 1. So it is unsymmetrical. And you are reacting this with a halogen acid, HX, where H is the hydrogen, okay, and X is the halogen. The hydrogen attaches itself on the carbon atom with more hydrogen atoms, with a higher number of hydrogens, and the halogen attaches itself to the carbon atom with a less number of hydrogen. And so the product here is R, C, H, and then the X is here, and then with C, H, CD. It is as simple as this. Now, if you put the X here, I will cross you in absence of a peroxide, and you put the H here, I will cross you diligently. I give you a smiling cross, so you can imagine how a smiling cross looks like. Okay? But what is the science still? Let's dig deep. If you attach, let's first remove that X. Okay? Let's first remove the X for a moment. So if you attach a hydrogen, we shall write the mechanism, don't worry. If you attach the hydrogen here, don't you see that you form a secondary carbocation or carbonium ion? And are you seeing that? This one and this one. That is a secondary carbocation. But if we attach the hydrogen here and this one remains 2, don't you see that you're going to form a primary carbocation? Good. Thanks for seeing that. So, did you remember what we talked about the other time concerning carbocations? The secondary carbocation is more stable than the primary carbocation. So that's why we add the H here and the X goes on this carbon atom and you form such a compound. Is that okay? Good. So let's write the mechanism. I'm going to erase everything so that we can get where to write. Now, let's say we are dealing with CH3, then CH, and then a double bond CH2, and we are reacting it with halogen acid. This one is easy. You don't need a lot of conditions. Just the halogen acid. We shall form. Write the product. If you write the product with me. Then this is CH. So where should I put the X? Okay, instead of using X, let me use the BR. This is CH3 and this will be our BR. So instead of using X, let me use the BR. So this is the HBr. Now the mechanism is simple, same thing. The H and Br have different electronegativity values. Okay? They have different electronegativities. So where the Br takes away the bonding electrons and becomes negatively charged, and the H becomes positively charged. Then from that, these pi electrons, they will be donated to the H, to the hydrogen, okay? And these bonding electrons between the hydrogen bromide bond, they are taken away by the Br. So now this is where the Machonicos rule is applied. So we shall form CH3, CH, and then CH, now 3. Now this one gains a gains a positive charge. Now if you form this at this stage, please, let me repeat this. If you form this at this stage, and then this is CH2, CH2. If you form this at this stage, I will cross you. This is not science. This is a primary carbocation, whereas this one is a secondary carbocation. And this secondary is more stable than a primary. That is Machonicos rule interpreted. Is that okay? So finally, if you form this, I will cross you. Let me even cross it so that you don't say, you might screenshot this and say that the teacher did it. So if you form this, I'll cross you. So then finally the BR, okay, comes in. Remember, it is negatively charged because it received these electrons. So it will donate these electrons to this carbon atom. Okay? And so you end up forming your final product, which is CH, which is CH3. Okay, are we together? CH, and then you have the BR here, you have the BR there, and finally CH3. As simple as that. This is Machonicos rule explained. Is that okay? Yes. So let me save this. Now, you can find in some books this when it is stated like this. They can state the same as this, that electron-rich compound of the reagent, this is the electron-rich compound, okay, of the reagent, adds to the carbon atoms with fewer hydrogen atoms. Are you seeing it? It adds on the carbon atom. It adds itself on the carbon atom with fewer hydrogens. Okay? While the electron, while with fewer hydrogen atoms bonded to it. While the electron deficient compound, which is the hydrogen, I didn't finish it. While the electron deficient compound, which is this hydrogen adds itself on the carbon atom with higher hydrogens. So basically, it is as simple as that. So illustration, I've already illustrated everything. Can you write for us the final products? Write for us the final product. Actually, you name, drop it in the chat box. Hurry up. Actually, I have a number of products. Write for us the final product. Apart from this, don't write this because you haven't studied it. It's what you are going to talk about. Don't write this because you don't know. Write the product here and the product here. I mark, then we go and do. You can also write the mechanism, but not now. You write the mechanism later. I think you have not given you work. So write the product, name the product, and you drop the name in the chat box. That's what I want to see. Hurry up, please. If it croaks, how do we make it? If it croaks, I've given you 2 minutes. If it croaks 3 here, we shall proceed. Don't write this. You can still continue and post. So here we shall form. It is an unsymmetrical alkene. So this is CH3. And then you have a double. Oh, we are writing the product. So it is an unsymmetrical alkene where this carbon atom, it has 1 hydrogen. Is it even 1? No, it has 1, 2, 3, and 4. So it doesn't have any hydrogen. Whereas this one has just 1. So this one has more hydrogens than this. So if you are reacting it with HBr, according to Machonicos Rule, the hydrogen attaches on the carbon atom with more hydrogens. So the hydrogen will go here so that you form a plus here. Then this Br comes and donates the 2 electrons. So the Br attaches here. So if you have this, oh my god. If you have this, bravo. If you don't have this, still there is something small to improve. And so when you are naming this is our carbon 1. So it will be 1. Now you don't need to include the 1. Just tell us, follow the alphabetical order. So this one becomes chloro, chloro. You don't need to write the 1 because 1 doesn't have any significance. Chloro, methyl, and then cyclo, because it is a cyclo compound. It is a cyclic compound. So this is cyclo. The whole of it is one word. And then cyclohexane, because they are 6 carbon atoms. Okay? Then this one is going to be, you added, so it is unsymmetrical. So the H goes here and the Cl goes there. So the product here is CH3, then C with a Cl. Okay? Hey, did I say chloro? This is, sorry for that. It is bromo, because it is a bromide. It is just a slip of tongue. So it's bromo. So this is Cl. And then there is a CH3 here. Okay, and then CH, and then so it is a CH2 and CH3. So when you are naming, this becomes carbon 1, carbon 2, carbon 3, and finally carbon 4. So this becomes 2 chloro because the C comes before the H. So it comes before the M. So this becomes 2 chloro. 2 chloro, another hyphen, 2, another hyphen, methyl. It's one word. 2 methyl. Then 1, 2, 3, 4. Butane. As simple as that. Is that okay? So nomenclature should be part of you. Naming these organic compounds, even if you are dosing like how, even if you are doing what, naming these organic compounds should be part of you. I think somebody has something to say.
Teacher,
Yes.
what about the hydro? You see on the cyclohexane,
Mm.
on the cyclo, there is there a hydrogen which should be on the lower what? On the lower carbon.
Mm.
Then how does it go away?
Okay, that's good. That's some pretty good question. Somebody is asking some good question that is good for us. So he's saying that that for this compound of ours, okay, CH3, if you add, you put the Bl, the Br, okay. So where does the hydrogen? Where has it gone? How has it disappeared? And the answer is simple. The hydrogen is there, okay? The hydrogen is there. Even the other hydrogen which was there, it is also there. So this carbon has 2 hydrogens. So writing this is the same as I can decide to show the hydrogens by putting here hydrogen, putting here another hydrogen. The same thing. Same thing. Okay, I can decide also to put here the hydrogens, so it is also the same thing. Okay, but if I put a double bond, okay, if I write this, I don't know if I've ever told you this, I can decide to write this in this format, or I write the carbons CH, C, C, and C. Now these are the same things, okay, they are the same. So where this is carbon, it must have 4 bonds, so has 4 bonds. So this carbon is the same as this, so this one also has 4 bonds, okay, 4 bonds. So this one, it also has the same story. This one has the same story. So this one is the same as this, so it has this hydrogen and this hydrogen. So this one, it has 1. The concept is 1 carbon must have 4 bonds, okay, 4 bonds. So even this carbon is this, so it also has 3 hydrogens. So I can decide to show the hydrogens, or I can decide to draw that condensed structure. It is all the same thing. So same story with this, okay, same story with this. So it is the same story, okay, same story. So it is as simple as that. So this one is what I've done here. So the hydrogen is there, but it is condensed. I've not shown it. But if I just do this, then it means this is a carbon atom, but there are 2 hydrogens. Is that okay? Yes. So in case you have another question, you are free to ask. You are free to ask. This is your lesson. You can unmute and ask. If there are no questions, Let me check your chat box. You never know. Now, this anti-Machonicos opposes the Machonicos rule. Okay? It is anti-Machonicos. So now, in presence of an organic peroxide, now the organic peroxide is this. It can be this, or any or this, as long as it is an alkyl group. It is a peroxide. Now, how do we write? Somebody might see this and get terrified. It is just CH3, okay, with O. Let me try to spread the bond with O, then with another CH3. So this is our organic peroxide. So in presence of an organic peroxide, now it is anti-Machonicos. The hydrogen attaches, the hydrogen from a halogen acid is added to the carbon atom across the double bond with a lower number of hydrogen atoms. And the halogen goes to the carbon atom with a higher number of hydrogens. It is the opposite. You shouldn't miss this mechanism because it is interesting. Okay? The mechanism is interesting. Okay? Now let's talk about it. Now the mechanism here is, okay, before I give you the mechanism, I can write for you an example. For example, we might say, we might have this CH3, and then CH, with O. I was writing it. Sorry for that. Don't miss this mechanism. If your neighbor is not sober, you can tap on your neighbor, okay, and say, neighbor, you are going to miss a lot. So we react HBr, okay, in presence of an organic peroxide. Okay, let me just generalize and say R or R. This one. Now instead of forming the Br here, we shall form CH. So here we shall oppose the Machonicos rule. CH, then you have the H2, and then the CH, and finally the Br here. Don't miss the mechanism. It is interesting. Okay? So, mechanism. Are you sober? Yes, that's pretty good. Now, this one undergoes what we call a free radical mechanism. Okay? Free radical mechanism. Where this peroxide of ours undergoes what we call homolytic fission to give you two radicals. Okay? Or you can say two alkoxide radicals. Let's say it is our R, O, then O, R. This. So this organic peroxide of ours is going to undergo what we call homolytic fission to give you this. Okay? And then this one also takes the one. This is what we call homolytic fission, where there is equal sharing of electrons. And so when you share, because it is one electron that is moving, you remember the other concept? So we use half arrows. It is, you get the full arrow and you divide this full arrow into a half. And then one points this side and another one points the other side. So what do we form? What do we form? We shall form two radicals, okay, of R or H with a dot. The dot is on oxygen. Don't use a circle, don't ring, okay? Don't write this. Some people will write this. I'll cross you. Do you know a smiling cross? I'll cross you. Now, after forming this radical, there are two of them. There are two of them. Now, these radicals, they are the ones that are highly reactive. So they are the ones that are going to induce a chemical reaction. Okay? And how is it going to occur? They are going to react. The R Our radical here, it will induce our HBr. Please, I hope you are sober. So you have a radical here, you have one electron here. So this one electron, it will be donated to this, and this hydrogen also will go with one electron and combine with this. Okay? And then the remaining electron will be taken by the Br. Is that okay? Yeah, that's pretty good. So what will happen? What are you going to form? You're going to form an alcohol, okay? ROH plus our bromide radical. Now this bromide radical, it is the one that will be highly reactive now. Okay? That will react, it is going to react with this bond. It will take away this one electron here. Let's do it. The Cr, the CH, let's do it. CH, with a double bond, and then CH2. That's pretty good. So the Br, okay, radical, it will come and take away one pi electron from this. Okay, so so that they combine, take away one pi electron. Okay, and then the other pi electron will be taken away by the carbon atom. Are we together? And so what shall we form? We shall form CH3, CH, that's pretty good, but this C is a radical. Now when you are writing on a paper with a pen and they combine like this, I will cross you. But since I'm writing with a laptop, you will excuse me. Then this is CH2, and the Br is going to attach on this carbon atom. Is that okay? Yeah, that's pretty good. And then now finally, this radical that has been formed, this one, it is the one that will react with a neutral molecule, okay, of hydrogen bromide. This is ugly. Let me rub. This is ugly. This is ugly. Sorry for that. So now, the radical that is formed, it is the one that will react with our neutral molecule of hydrogen bromide, okay, to take away this hydrogen. Are we seeing? Okay. And then to take away, let's do this. The arrows are too long. Then and then this Br is taken. Is that okay? So what shall we form? We shall form our CH3, CH3, then CH2, there is a 2, and then the CH2Br. So that is our final product. But there is always a chain termination step. So we cannot stop here, that you formed your final product, that you stop here. You still have these radicals. Okay? You still have these radicals in your reaction vessel. So you cannot stop. The reaction cannot stop at that level. So what is going to happen? The radical of Br that is formed, okay, it will react with this. Sorry. It will that is our radical. It will react with this. Okay, so I have no problem if I write it like this. O R. It is still the same thing. It will react to take away this. Okay, and you form your radical back. Okay, and so we shall have our HBr, HBr plus our alkoxide radical, R radical. Then finally, the last step is the radical, the R OH, sorry, the R, okay, combining with another radical, okay. Here we shall synthesize our radical back, okay, so that this one combines with this electron, okay, to form our peroxide back, R O R, and that is that simple mechanism. The reactions of alkenes in presence of reaction of water in presence of an amino acid, or you can say acidified water. This is simple. If you know that where we have reached so far, this reaction becomes easy for you. So when an alkene is heated with water, okay, in presence of an acid, could be sulfuric acid, then we shall form an alcohol. And this reaction is so important in organic synthesis, okay, where you are required to prepare an alcohol, and then from an alcohol you form something else, depending on what you want. So it is known as a hydration reaction. Why? Because you are reacting it with water. Hydration means addition of water, whereas dehydration means removal of water. Remember when we were forming alkenes from alcohols, it was dehydration. Now this is most something like a reverse reaction, okay. So you can prepare alcohols from alkenes and alkenes from alcohols. So this is it. Still our Machonicos, the same thing. So here we shall form the OH goes here. If you put the OH here, I will cross you. I'll give you a smiling cross. If you put the OH here, I'll cross you. So the product here becomes, you can be naming it, CH. You can write your product and you compare your product with mine. This becomes OH, and then H. So this is a secondary alcohol. We shall study alcohols and talk about classes of alcohols. So when you are naming, therefore this one becomes propan, propan, hyphen 2. Now here you cannot neglect the position. You must show. And how do you show it? You write propan, you put hyphen, then you write a 2, you put another hyphen, and then or. And that's how we name alcohols. So if you don't do this, if you name this is the IUPAC name. Away from this, that is your name. It means that you have invented your name. Now the mechanism, it is simple. We have done enough mechanisms. We can't fail to do this. So the first, these hydrogen ions, they will take up the pi electrons from this double bond. So you end up forming a secondary carbonium ion. So CH3, CH, double, CH2, the hydrogen ion, it is going to take the pi electrons. This one is already an ion. In other words, it is a catalyst, okay. So that you form CH, that's pretty good, CH3. Now if you add the hydrogen here and put a 2 here, I'll cross you. Why? Because you form a primary carbocation which is unstable. You have already seen this. Then CH3 with a plus, okay. And then after forming this, now this is an electrophile. Now water comes in, because water is a good nucleophile. The oxygen has 2 lone pairs of electrons, okay. So it will donate 1 lone pair, okay, is going to be donated. Now some of you you just want just a straight line. That is wrong. At least curve it a bit, but don't overcurve. Okay, so it will donate a lone pair of electrons to this carbon, and so we shall end up having CH, CH3, CH, CH3, okay, but the O has 3 bonds. Oh, it has this, and it also has this. So this O is agitating. It is crying. O must have a maximum of 2 bonds, 2 covalent bonds, but this one has 3. So to balance that, then you put a plus on oxygen. This plus shows that oxygen has lost 2 electrons. Okay, so as a result, to balance this charge, then the oxygen is going to end up taking the 2 electrons in one of the oxygen hydrogen bonds. Okay, so as a result, what do you form? What do you form? What's wrong with my pen? What do you form? Yes, that one. We shall form CH3. That is a 3. Then CH. Then CH3. Okay, and the OH. Then here you put loss of a proton. We have lost a proton, and that's how we write a proton. Now really, what is wrong? What stops you from writing such a mechanism? What stops you from being as neat as this?